Hi, my name is Evgeny, and in this video I'm going to familiarize you with what I call my professional and academic triptych. Well, you might ask me, what is a triptych? Well, triptych is a piece of art which consists of three main parts. However, these three main parts are supposed to be treated and appreciated as one single piece of art. Well, my triptych consists of design thinking, research methods, and cognitive science. Well, these three might seem unrelated and unconnected. However, in this video, I will try to connect them all. The first part of my triptych is design thinking. We are surrounded by objects. Most of the objects suggest interaction. It is designer's main priority to make sure that this interaction between the user and the object is as smooth as possible. One of the most influential books in design is called The Design of Everyday Things by Don Norman. In this book, Don Norman introduces 7 fundamental design principles. So those 7 fundamental principles of design are affordance, signifiers, conceptual model, constraints, feedback, mapping, and discoverability. We're gonna start with affordance. Affordance is also known as an is-for relationship. This is a relationship between the capabilities of the agent and the properties of the object. This relationship simply determines how the object could possibly be used. We're gonna take this nice wooden table as an example. So the table surface suggests putting objects on the table. You could also use it as a bed to fall asleep after a long assignment at the university. See you tomorrow. Well, next principle in line is called signifiers. Well, signifiers are used to communicate to the user the proper behavior that can be done. Unlike affordance, it's not a relationship. Those are the properties of the object. Those are the designation of which, how, and where the action is supposed to be done. They're also known as hints and clues that help the user to understand where, how, and what action they can do. Let's take this lens as the next example. The two main affordances of the lens are to focus and zoom in and out. In order to signify those affordances, the manufacturer provides us with a set of two rings. The first one is used for focusing, and the other one is for zooming in and out. Those are the signifiers. Let's take this pen as the next example. The blue pen provides us with the following affordances: to grasp, to write, or any other action that you can think of. Let's take affordance of writing. The manufacturer provides us with this blue rubber that suggests where exactly we're supposed to grasp in order to have the best possible writing experience. The next one is a conceptual model. Conceptual model is a rather simplified explanation of how the system works. While a proper conceptual model helps the user to predict a possible behavior from the system. Well, it's fair to say that the conceptual model doesn't have to be precise and accurate. Let's take the lock as the next example. As you can see, the system is quite complex. However, it's not necessary to understand the entire system. We don't need to know what happens in these parts to get the job done. All we need to know is when this cylinder is rotated, the shank gets released. The next principle is known as constraint. Constraints are used to prevent the user from making a mistake. Basically, they limit the user within the right path so that the user do not make any mistakes. Well, it's not possible to make no mistakes at all. However, the constraints are trying to minimize the risk of a mistake or an error. Let's take these cables as an example of constraints. We have two cables, an HDMI and the USB cable. So as you can see, both cables are provided with metal heads. Not only do the metal heads protect the vulnerable sensitive contact part of the cable, they also prevent me from inserting HDMI cable into USB port and the other way around. Basically, by providing different shapes of the metal heads, the manufacturer prevents me from confusing the cables. This type of constraint is also known as physical constraint. The next type of constraint is known as semantic constraint. The constraint here is delivered with the help of the meaning. In this case, we have a traffic light. We understand that there is a certain meaning behind each color. For example, the red light means that we must not cross the road because it's dangerous, since the traffic is on. The next principle is known as feedback. Feedback is a simple way to let you know that the system has started working on your request. Well, feedback is of a great importance because it helps the user to understand the current state of the system. Designers have to make sure that the feedback is delivered in a timely manner. Let's take this multiple socket as the next example. The socket has two main states, on and off. How does the system inform the user about its current state? Well, its state is shown with the help of this red button. Whenever we change the state of the system by pressing the button lights up to show the on state or turns off to show the off state. This is the feedback. The next principle is mapping. Well, this term comes from mathematics. Basically, it means relationship between two elements in two different sets. Well, this includes the design and layout of the controlling elements and the controlled ones. The principle of mapping goes hand in hand with a spatial analogy. Let's consider a regular cooker as our next example. As you can see, there are two sets of elements, the controlling and controlled ones. In this case, the principle of spatial analogy is very well applied, because the layout of the controlling elements clearly corresponds to the layout of the controlled ones. Well, final and the central principle of design is known as discoverability. The system should allow the user to discover its functionality. Now it's time to discover these principles applied in the digital user interfaces. Just like the table surface, the working area in Figma suggests us the following actions. To put objects on it, or you can just type a piece of text here. Here is an example of signifiers. The fill color menu suggests the following affordances, changing opacity or color, but the affordance would not be clear if we didn't have the signifiers here. Here is a web page as a next example. The page suggests the following affordances. We can scroll, press the buttons, navigate, explore, or search. However, there are certain objects that inform us about the certain affordances, just like the small arrow that points down in order to suggest us the following action. Scroll down or press it in order to arrive to the next page where we can get some more information about the product. In this case, we have a Tesla car. Let's take a conceptual model implemented in a messenger. By pressing the paper plane button, we send a message. Even though this representation is not accurate, since conceptual model does not really reflect what's actually happening on the program level, it is still appropriate, because it helps the user to understand what's going to happen if we press this button. We send a message. Here's an example of constraint in an editing software. Whenever we want to close the window, the system notifies us that we haven't saved the project yet. That way, the system prevents us from accidentally or mistakenly closing the window, making sure that the project is saved. Here is a very simple example of a feedback. If I press Add to Cart and the item has successfully been added to my cart, the system notifies me by showing me a message. This is a feedback. Let's take a regular map as an example of mapping. It's quite simple. There is a clear and accurate correspondence between the two sets of elements, the real cafe places and the marks on the map. In this case, we don't have controlling relationship between the elements. However, the system clearly shows us which of the markers corresponds with the real cafe places in the town. Or an example of a split display. When you have two displays connected to your computer, you can navigate between them. So the two elements on the screen here correspond to the two monitors or displays that you have connected to your computer. In other words, those elements are mapped to the real monitors or displays. This is another example of mapping principle. Well, I think it's time for a coffee break. While I'm having this nice cup of coffee, you'll have to complete a couple of exercises. Please read the instructions attentively and do the exercises. See you later. Oh, you're done. Great job. So the learning material that was given at the very beginning of this video and the subsequent set of tasks that you have just completed are part of a huge theoretical body known as worked out examples. Well, you might ask me, what is a worked out example? A worked out example is an instructional method based on a problem statement and the subsequent solution steps or key features that help you arrive at the desired problem state. Instruction based on the worked out examples can be subdivided into two huge subgroups. The first one is learning from correct worked examples, and the second one is learning from incorrect worked out examples. You might say, well, why would you want to learn from the incorrect worked out solutions? In reality, both of these types of worked out examples are equally applied in practice. Well, that's because in some conditions, the incorrect worked out solutions are proven to trigger deeper self-explanation. And it's fair to say that self-explanation happened to be the central notion in the theory based on the worked out example solutions. Well, self-explanation is also known as constructive self-instruction. Basically, it's a conversion of learning material into your own words and then into your own knowledge and set of skills, which can be applicable in a problem situation. Well, simply put, self-explanation is nothing but paraphrasing learning material into your own words, which makes the learning material more understandable for you. That means that deeper self-explanation can lead to a deeper understanding of the learning material and, as a result, can lead to a better learning outcome. That is why it's of great importance to trigger self-explanation in a learning process. Well, self-explanation can be prompted on different levels. You have already experienced self-explanation. Remember the task that I gave you? Well, that was self-explanation. The type of self-explanation prompt that was used in this video is known as scaffolded self-explanation prompt. It's a bit different from open-ended self-explanation, where self-explanation is triggered by asking you a question and when you have to openly paraphrase the learning material. In the scaffolded version, you are provided with a set of examples and a set of vocabulary where you have to complete the gaps using this predefined set of vocabulary. It's a rather shallow way to self-explain, however, it is still self-explanation. Now, all of these notions happen to be part of my research topic. The research topic is learning from correct and incorrect worked examples. Well, what I test two different groups with correct and incorrect worked out examples. Then I prompt self-explanation, and then I see which of the groups will provide me with a deeper self-explanation. In my case, self-explanation is open-ended. Basically, I will ask them to self-explain. They will not have any predefined set of vocabulary. They will have to actually self-explain, write a comment. And then I test the learning outcome. Besides that, I also test the cognitive load, which is a central theoretical background in any cognitive research. So it's time to talk about cognitive architecture.
There are two substructures within the human cognitive system. Learning takes place when information enters working memory, gets processed in it, and then is integrated with the prior knowledge from the long-term memory. The process is also known as schema construction. After a schema has been constructed, it is stored in the long-term memory. Long-term memory is believed to be unlimited, whereas working memory is believed highly limited. Since learning cannot take place without working memory, instructional designers have to take great care of the working memory, because it is vital for successful learning. There are three types of cognitive load. The first one is extraneous, the second one intrinsic, and the last one is germane. Extraneous cognitive load is associated with irrelevant information, such as the format of the learning material. That can be the color of the presentation or the font size. The intrinsic cognitive load is associated with the subject matter. This kind of cognitive load can be caused by the complexity of the subject. And the last but not least, germane cognitive load is associated with the learning. In other words, with the schema construction, that is the effort that the learner has to take in order to construct the schema, to integrate and process the new coming information with the prior knowledge.
So in the meantime, we have reached the end of this video. So it's time for conclusion. At the very beginning of the video, I said, this is my professional and academic triptych. So the first part of the triptych was design. So I tried to focus on instructional and interaction design and follow the main principles. The second one was research. All the decisions that I make are based on empirical evidence. The last but not least is a cognitive architecture. Since we design products for people, we have to be human-centered. And to be human-centered is to take into consideration all the shortcomings and weaknesses of people's cognitive architecture. Based on this triptych, I'm trying to reach my professional goal. I'm searching to create innovative multimedia content for a meaningful learning experience.